Good afternoon, Year 7. So, today we're basically going to have a revision lesson for our test tomorrow. Now, obviously that test has been pushed back a few times now because of this COVID thing. We're going to get it out of the way tomorrow, and so today is just going to be a solid revision session. There are a few different types of tasks in there, so hopefully it won't be too tiring or boring. We're going to work our way through all 6 topics you need to know. So, we'll start with biology. Biology D. Now, biology D is variation. Variation is a nice, simple, straightforward topic with some key things which you just need to work through very quickly. We can get this one out of the way very early on. Now, in there, you need to know what variation is. Now, that's something I'm going to ask you to cover yourself. To be honest, that's the easiest bit, and so I didn't want to waste too much time for people going back over it. As long as you understand about inherited variation and environmental variation, you will be fine. And the next thing is adaptations, what they are, how different organisms might be adapted, and how they might increase survival, selective breeding, and natural selection. And that's what we're going to focus on. So the first thing is adaptations. Now, why is that not working? There we go. Put 2 animals on the board, and what I'd like you to do is I'd like you to write down 3 adaptations for each animal, and explain why those are good things for that animal. Why those are good things for that animal. So pause me now, just pause this video, and explain you need to write down camel, 3 adaptations, why each one is good, penguin, 3 adaptations, why each one is good. Okay? There's no need particularly for full sentences in this because it's just a quick revision before this test. So pause me. So, hopefully you now have 3 adaptations for each organism written down and why each of those is a good thing. If you've not written them down, go back and write them down. I'm telling you to do that because it will be helpful to you. So, with the camel, there are a few we could talk about. The first and most obvious one is the hump. Now, everyone thinks the hump is full of water. It's not full of water, it's full of fat. It's full of fat because we can do respiration, which we don't know much about at the moment, but by doing that, we can break the fat down and release water. So if you feel a camel's hump, it is not watery, it is fatty. It's full of fat, which is used to release water for the camel. You can talk about the long eyelashes for keeping sand out of his eyes. You could talk about the large splayed feet, so he doesn't sink into sand. You could talk about thin fur and lack of sweat, so he doesn't overheats. You can talk about his small surface area, small surface area to volume ratio, so that he doesn't absorb much heat. All of those are good. You could talk about the colour of his fur, so he blends into the sand, avoids being eaten by predators, whatever predators there are out there. I'm sure you've all come up with others as well. If there are any that I've missed, as long as they are correct, you're welcome to check it on the internet, and that you've got a good reason for them, perfectly acceptable. The penguin a little bit more difficult. So we can talk about how penguins have lots of blubber, lots of fat to store that heat inside of them. We can talk about how they have waterproof feathers. So if you drop a normal bird into water and leave it there, it will sink very quickly because its feathers will get waterlogged. Not with penguins, obviously. They have waterproof feathers covered in oil. You can talk about their streamlined shape, so they can swim easily through water, so they can catch fish. Talk about their flippers and how they are better adapted than normal wings for pushing through water. You can talk about their non-furry feet so that they don't absorb any melted ice into their feathers. That will do for me, to be honest. If you've got any others, again, as long as they're correct, that's acceptable. Now, one thing we didn't do is talk about behavioural adaptations. So we talked a lot about structural adaptations, changes to your body, but we should know that there are other kinds of adaptations. So you could talk about how the penguin is going to huddle together in large groups. That will be a behavioural adaptation. A change in their behaviour enables them to survive better because it enables them to store heat. So when you talk about adaptation, you don't always have to be talking about body adaptations. You're talking about changes in their behaviour as well. Fine. Now the next thing we need to know about is natural selection. So natural selection is, according to modern scientists, how modern animals got their adaptations. Now that's at the moment only theory, but it's a fairly well tested one at the moment. So the question then is, according to natural selection, how did the camel get its hump? How did the camel get its hump? So what I'd like you to do is like you to pause me, I'd like you to write this out in full. It's usually worth around 4 to 6 marks, so there's a lot you can write here. I'd like you to write down everything you know about how the camel got its hump according to natural selection. So, hopefully you paused me. If you didn't pause me now, get that written down. Now, how did it get its hump according to natural selection? So, what you have to understand is, first of all, that the hump is an example of inherited variation. Alright, the reason it has a hump is because it has changes in its genetic material it got from its parents, its DNA, which enable it to grow a hump. Alright, if I put hump DNA into another organism, I could make it grow a hump. It's DNA. Okay, so the first thing is, one day, the original horse thing that became the camel, one day one is born, a baby horse thing is born with a little tiny hump made of fat because of a change in its DNA. So there's two things there. It's got a change in its DNA, which has led it to have a little hump. The second thing to say is that that hump will allow it to survive better because it's got loads of fat in it on its back. You can break down that hump and release water. So we've got a positive change there. That enables it to survive longer. Because it survives longer, it has more children, has more offspring, if you like, and it passes on this hump DNA to its offspring. So most of its offspring will also have a hump. They too will also survive longer than the other horse things. And so eventually, if you give it lots and lots of generations, because they survive better and they have more kids, eventually there will be more humped camels than not humped camels. Camels with humps. Now, what will then happen is that after a few thousand to a few tens of thousands of years, we will have a whole group of organisms, all of which have a little hump on their back. And then one day a camel will be born with a bigger hump. And that too will survive better, have more offspring. And so over the course of many, many, many millions of years, you end up with this kind of a thing. This giant hump. Because every time a camel is born with a bigger and a bigger and a bigger hump, that camel survives better and better and better. So steps. 1, changing the DNA. 2, leading to a hump, which causes it to 3, survive better, so that 4, it has more offspring, and 5, it passes on its hump DNA to its offspring, so that 6, it will spread through the population, this DNA. Fine. If you didn't get any of that, just go back 30 seconds, listen to me say it again, or check your notes and make sure you got it correct. If you didn't get it correct, go back and make sure you know natural selection. You need to revise from your notes, or go through bite size, and make sure you know natural selection. Now, the final bit was selective breeding, and really there's only one thing to say about that, and that is, how do we do selective breeding? So, describe how I could selectively breed a very friendly dog. So I'm saying to you, I give you some normal dogs of varying friendlinesses, and I want the most possible friendly dog. I want the least aggression, I want the most kind of wanting to sit with me and watch TV. I want a friendly dog. How could I selectively breed one of those? So again, pause me and answer that question in full. So, hopefully you paused me. If you didn't, pause me now, get this done. Right, selectively breeding friendly dogs. So I give you some dogs. Right, how do we do this? First things first, first step, pick the friendliest female dog and the friendliest male dog. And that's the first step. Step 2. Get them to breed together. Leave them in a room together, put on some mood lighting, get some candles, leave them to breed together. And hopefully they will make some puppies. So what you want to do is come back and get these puppies. And these puppies need to grow up a little bit. You need to decide which of these puppies are the friendliest. Because at this point we have not done any selective breeding. Not really. We're going to have a load of puppies, some of which will be very friendly. Yes, great, because we had a friendly mum and dad. But some of them will actually not be very friendly. That happens. Sometimes two people with brown hair have a blonde-haired baby. That happens, okay? So sometimes you're not exactly like your parents. So we're going to have some friendly dogs, friendly puppies, and some not friendly puppies. What we do is we get the very friendliest puppies of these very friendly dogs, and we breed them with other friendly dogs. And we don't let the not friendly ones breed. We give them to other people to look after. We breed the friendliest with the friendliest. and then they will have puppies. And again, we do the same thing. We take the friendliest puppies and we breed them with other friendly dogs, and we take the not friendly puppies and we give them away. Do that for generation after generation after generation, only letting the friendliest puppies breed, and you will have a friendly dog. So, stages. 1. Pick friendly dogs. 2. Breed them. 3. Pick the friendliest puppies of those friendly dogs and breed them with other dogs that are friendly. And 4. Repeat for many generations, lots and lots and lots of generations. You do it for 2, it won't stick. You do it for lots and lots and lots, it will stick, and you will end up with very friendly dogs. And this is only how we got dogs. Wolves are not friendly. So when people first started breeding wolves to get dogs, they didn't have friendly wolves. What they did was they got the friendliest of the wolves and they bred them together. Until nowadays we have dogs that are mostly pretty friendly. Alright, fine. So, if you didn't get any of that topic at all, go back and redo it. Do it again. Right, that was all a bit dry, wasn't it? So we're going to do something a bit more relaxed now. Because with any revision session, you've got to do periods of intensity followed by periods of kind of more relaxed revision. So we're going to move through all of this. We'll come back to it later. All of this later. We'll come back to it. I'm going to go up to Earth in Space, which is Chemistry E. So we're going to do all 6. We're going to do them in a random kind of order to make a bit of a mixture of different types of tasks. Chemistry E. Now, Chemistry E is all about space. It's a really nice topic, and we just did it, so I expect it to be kind of fresh in your mind. Now, we pushed it a little bit beyond where we needed to push it. Right? Now, you need to know how the solar system works. So what is the solar system? What's in the solar system, and what we know about the solar system. We need to know about day, nights, and seasons on Earth and how they work. We need to know what a light year is. We talked about it. We need to know what the universe is made out of, so what's inside the universe. And we need to know how space exploration can be carried out. So we talked about that a bit, the lesson before you left, and a little bit on the last lesson. Now, what I'd like you to do, it's always a good idea to be a bit creative in revision. There is nothing wrong with taking some time out, assuming you've got it in your revision schedule, and just being creative. So, a bit of a poster creation. Now, what I'd like you to do is I'd like you to focus on the space bit of space. If you don't know anything about the Earth bit of space, you can go and revise that yourself. There's nothing wrong with that. There will be time during this lesson for that. What I'd like you to do, I'd like you to create me a poster, or at the very least a storyboard, something creative about space. And it needs to incorporate the solar system, what's in the solar system, and maybe some facts about the different planets might be interesting, that might be nice. What a light year is, so you need to get that fact in there somewhere, just scratch it in there somewhere. And how we can explore space. So the space bit of space, I need you to write down in this poster or storyboard or something creative. Spend some time on this, spend a good 20 minutes on it. Just relax and enjoy it and try and get some facts in there. Check over your space notes in your book, make sure you didn't miss anything. Check over your your bite size if you've got access to that, make sure you're not missing anything, and just make sure that you know what there is to know about space. Right, so relax and get on with that. Have 20 minutes, just pause this video, put me to one side, and the moment you finish this storyboard, poster kind of a thing, bring this video back, and we're going to do a little bit more dry revision on other stuff. Okay. So hopefully you've enjoyed doing that. I'd like to see these posters, I'd like to have a look at them, I'd like to see what you're doing. Physics D then, energy cost of transfers. So, this is quite a difficult one in all honesty. And it comes up quite a lot, so I anticipate it being on your test quite a bit. Now, this is all about different types of energy and where we get them from. The first bit, the energy stores bit, people always forget about it. So this is about the types of energy that are found in objects. We need to know about conservation of energy, the idea that we're not going to lose energy. We need to know about Sankey diagrams. And then this last bit people do tend to remember, which is how do we make energy. So, we'll start like this. In fact, this is pretty much what we're going to do. I'd like you to pick out the energy transfers associated with these events. Now, if you don't know what that means, let's say I take, I don't know, this pot and I drop it. Right now it has gravitational potential energy. When I drop it, it gains kinetic energy, and that then turns into sound and heat energy. So, in my book I would write gravitational potential energy, arrow, kinetic energy, arrow, sound energy. And that's how I would write that. So can you do that for all four of these things? Alright, what energy do we start with? What energy do we end up with? Is there an intermediate energy? Right? So, pause me and do those first four, and then we'll talk about Sankey diagrams afterwards, if that's alright. Right, hopefully you paused me, hopefully you've done. So, climbing the stairs. What kind of energy do we start with? Well, we're climbing the stairs, I'm assuming it's a human being climbing the stairs. Where do we get our energy from? We get our energy from the food we eat, chemical energy. We've got chemical energy to start with. All human beings start with chemical energy. That then gets turned into kinetic energy. We're going to use our movement to climb up the stairs. And as we climb the stairs, we turn our kinetic energy. Where does that go into? It goes into gravitational potential energy. So, chemical energy, arrow, kinetic energy, arrow, gravitational potential energy. Right? Throwing a ball straight up in the air. So I got my ball, I throw it straight up in the air. Right, first thing, where do I get my energy from? Chemical energy again. Don't ever miss this first stage. I'm throwing the ball, I need chemical energy. I turn that into kinetic energy. Up in the air it goes. That then turns into gravitational potential energy because it's in the air, which then turns back into kinetic energy when it falls back down. So, chemical energy to kinetic energy when I throw it up, to gravitational potential energy as it gets to the top, back into kinetic energy as it falls back down again. And you can add sound energy when it hits the ground if you like. Arrow, 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 arrow. Stretching an elastic band. Where am I getting my energy from? Chemical energy. So I stretch it, and it creates elastic potential energy. It's one we don't talk about very much. But when you stretch a spring, or you stretch an elastic band, or anything that's stretchy, you're transferring elastic potential energy. Chemical energy into elastic potential energy. Fine. A wind turbine powering an electric light bulb. Well, that's kinetic energy in the wind and the turbine turning into light energy and heat energy. Fine. Now, draw a Sankey diagram for these outcomes. Okay, Sankey diagrams. If you don't remember what a Sankey diagram is, you need to go back and look that up, because it's something that does come up. And I'd like you to draw a Sankey diagram for these three things. Now, I'm not expecting you to have squared paper at home to make it roughly correct. In an exam, I'd expect you to measure exactly how wide the arrows should be. But if you don't have that at home, if you don't have a squared paper at home, that's fine. Do it roughly using a ruler. Now, there's three there. You need to have a go, draw the Sankey diagrams, and we'll go through the answers after you unpause me. Fine. So, electric heaters. Take in 150 joules of electrical energy, give out 50 joules of light energy and 100 joules of heat energy. Well, the first thing we have to understand is which is the useful energy. That's the heat energy. So the heat energy goes along, and it should look like this up here, the white one. Electrical energy in, turns into thermal energy, 100 joules, and this should be the light energy down here, 50 joules. Fine. A light bulb gives out 75 joules of light energy and 25 joules of heat energy. This is this one here. Again, the light energy now is the one that is the useful one. So electrical energy, 100 joules in, light energy, 75 joules out, and heat energy, 25 joules out. And the final and hardest one, I would argue, the hairdryer, takes in 100 joules of electrical energy, gives out 30 of kinetic, 50 of heat, and 20 of sound. Now, which are the useful ones here? Kinetic is useful. I'm turning the blades of my fan, which makes the wind rush out of it. 50 joules of heat, that's useful. I want to blow hot air. 20 joules of sound, it is not useful for it to go, that's not useful. If I could stop it doing that, I'd waste a lot of energy. It's not easy with a fan going around, though, to stop it releasing sound. So, we've got 100 joules in, which they've made 50 squares. So they've used 2 joules per square, if you like. 15 squares then, or 30 joules of useful energy, of kinetic energy, 25 squares or 50 joules of heat energy, and 10 squares or 20 joules of waste sound energy. Now, this is a fantastic example, it's the best example. This is the kind of thing you'd be drawing in your tests. You'd be making sure the size of the arrow was relative to the amount of energy. So you decide, well, 1 square per 10 joules, 1 square per 1 joule, 1 square per 2 joules, you're going to keep it the same. So if you've got 50 squares here, it's 100 joules of energy. Then if you want 30 joules of energy, you need 15 squares. It has to be relative. And this is the kind of thing I expect you to draw in a test. Now, there is other stuff on this topic, and I'm not going to say there isn't, about the generation of electricity. But most people tend to get that better. So if you don't get that, if you don't remember that, just go back and have a look at your PowerPoints on student resources, or go back and have a look in your book to remind yourself about that. But mainly you want to focus on, for today I think, energy transfers and Sankey diagrams. Not because I know that's what's going to be on the test, because I know people tend to struggle with that. Okay. Now we're going to do back to biology again. All the way back to biology. Did that, didn't we? Right. Ecosystems. So, ecosystems is again a nice, easy topic. The biology on these 6 topics is pretty much the easiest bit, I would argue. So, let's do some ecosystems. You're talking about what is an ecosystem? You're talking about sampling techniques, food chains, food webs, bioaccumulation. Those are all relatively complex, but when you actually go through them, they're not too bad. So let's have a look at some questions about this. Right, I'd like you to draw me a food chain. That's the first thing. There's a food chain. I'd like you to draw it, and then there's 3 questions. Hopefully nice and easy. And yeah, I mean, I'll let you get on. You need 4 minutes for this, maybe? Pause me and have a go. Right, hopefully you paused me and had a go. Well, first things first, we have to know what eats what, right? But the answer is the golden algae comes first. The golden algae is at the beginning. Then we have an arrow running from the golden algae to the shrimp. Now, this is the first mistake people make all the time. They have an arrow running the wrong way. They run the arrow from the shrimp into the golden algae. The arrow points towards the thing that is eating. It points in the direction that the energy is going. So if you have an arrow pointing from a shark to a seahorse, you are saying the seahorse regularly eats the shark. That is not a thing. That's not a thing. So it needs to go shrimp, then an arrow pointing to, it needs to go golden algae, then an arrow pointing towards the shrimp, then an arrow pointing towards the seahorse, and an arrow pointing towards the nurse shark. Now, if you thought shrimp ate seahorses, if you genuinely thought that, fine. I'm not expecting you to be a seahorse expert, right? But you have to know that whatever is eating has an arrow going towards it, right? What do the arrows in your food chain represent? Really important question. You might write, well, what eats what? Not really. They do, kind of. What they're really showing is where the energy is going. So you start with the energy in the algae, the energy then goes into the shrimp, it then goes into the seahorse, it then goes into the nurse shark. The arrows represent the flow of energy, the transfer of energy. Label the trophic levels. Well, the first trophic level, the trophic level is just where we are on the food chain. The first trophic level is the golden algae. The second is the shrimp. The third is the seahorse, and the fourth is the nurse shark. And then the labels, well, the golden algae is a producer. The shrimp is a primary consumer. The seahorse is a secondary consumer, and the nurse shark is a tertiary consumer. And where does all this energy come from initially? It doesn't come from the golden algae initially. Golden algae aren't created with loads of energy. They don't just create energy out of nothing. It comes from the sun. Almost all energy in every food chain comes from the sun. Now, there are exceptions. There is a food chain, lots, on the bottom of the ocean where there is no sun, which starts off with chemical energy coming from thermal vents from under the ground. But on the land, all of the energy comes from the sun originally. Right. Okay. 6 marks here. Now, again, these are just questions. We're going to do questions for this topic, and then we're going to do something slightly different for the other topics. So, 6 questions here I'd like you to have a go at, and I'd like you to, again, just write down your answers in your books. If you didn't pause me, do. So, hopefully you got to do this. Depends how rainy it was on the days when you were doing your ecology. How could I determine whether dandelions grow most frequently on the field near the girls' school or the boys' school? Now, some people have done this in their classrooms, some people have gone into the field. This is all about quadrats, right? Quadrats. So those quadrats are those kind of square things, bits of metal. I should have brought one with me, shouldn't I? It's with lines down the middle, and they're used to count plants or very, very, very slow moving organisms. Animals. So what you would do, you would go out and you'd place quadrats on the boys' side of the field and on the girls' side of the field, and you place them as randomly as you could, just kind of spread out over the boys' side of the field and the girls' side of the field. You would count how many dandelions grow on the boys' side of the field in each quadrat. So you'd say, well, this quadrat has 10, this quadrat has 4, this quadrat has none. You do that for the boys' side of the field and the girls' side of the field. You might do maybe 10 repeats. It's important to do repeats. So you might do 10 quadrats on the boys' side of the field, 10 quadrats on the girls' side of the field. You would take an average. So say on average there are 1.6 dandelions per quadrat on the boys' side of the field. There's 31.6 on the girls' side of the field, because girls' side of the field emits happiness and joy, and the boys' side of the field emits pain and suffering. No, maybe not, but we will see which one has the higher average, right? And whoever has the higher average, that's where it grows most frequently. It's as simple as that. So, one more time. You'd use a quadrat. You'd place the quadrat down roughly randomly on the boys' side of the field and the girls' side of the field. You'd do it maybe 10 times, so it repeats. You count how many dandelions there were in each quadrat, and you would take an average per quadrat. So you add them all together and divide by the number of quadrats. How could I find out what insects there were in the copse? Right. There are loads of ways of doing this. You can set yourself little pitfall traps. You can dig yourself a little hole. You can wait for the insects to fall in. You could use a pooter, a little bit of equipment you use to suck up the insects. You can store them in little plastic pots. Or you could just go around with a net and catch them. Either way, that's the kind of thing. Which, what I don't want people to say is about quadrats. Because you don't use quadrats on insects because they will just run or fly away while you're trying to count them. Right. We'll do one more. We'll do this one. And then we'll do something different. So, why might a farmer want to use insecticides? What is bioaccumulation, and why might insecticides be very dangerous for large animals such as wolves? So again, final question for now. Can you write down the question and the answer? No, excuse me, you just write down the answer, not the question. That's what I was trying to say. So, what did we say here? Why might a farmer want to use insecticides? Firstly, the reason is because insects eat his crops, his plants, and therefore he makes less money because they eat all of his crops, his plants. What is bioaccumulation? Bioaccumulation is the idea that each insect will only eat a small amount of insecticide. But then a mouse or a bird will come along and will eat a lot of those insects. So they will have lots of insecticide inside of them. And then maybe a wolf or a cat or some other predator comes along and eats the mice, and the birds, maybe they eat lots of mice or birds. Well, each mouse had lots of insecticide in it because it ate lots of insects which had insecticide in them. And therefore, if the cat eats lots of mice, well, we gain lots of insecticides inside of the cat or the bird. And so it's the idea that insecticides travel up food chains and they become more and more concentrated as they go along. Why might it be very dangerous for large animals such as wolves? Well, because they are going to be eating lots and lots and lots of insecticides just by eating the smaller animals, which then ate the insects. And so they can die. And actually, in terms of nasty chemicals like DDT, which was used in a lot of places, but in America quite frequently, it ended up killing lots of things like bald eagles and golden eagles. because they were eating lots of mice, and the mice ate lots of insects, and they all had insecticide in them. Right, we'll leave that there for now, and we'll go to the final physics topic, I think. Waves and sound. Now, waves and sound are it's not too bad. It's not too bad at all. But there's a lot there. And so rather than ask you questions, I'm going to go away and do some independent revision. It should be a bit more fun and interesting anyway, because it enables you to target things you don't know very well. So what I'd like you to do, I'm going to do some flashcard creation. And teach yourselves how to do that. First things first, you need some squares of paper. Now if you have some scissors, that's great. If you don't have some scissors, it might just be a question of ripping, sadly. You are welcome to use my book. The last 2 pages of my book that are free. Just cut them out if possible. If you have to rip them out, because we're at home, rip them out. I would give you paper in school. We don't have any opportunity to do that at home. So cut them into little squares. You'll have to write a little question on them. You just go through your topic and find all the important facts, maybe starting with the ones you don't know. So literally work through your notes or work through the PowerPoints on student resources. Starting with the bits you find most difficult, write down all the important facts. So one important fact is that sound cannot travel in a vacuum. Well, that's an important fact. I say write them down, I apologise. Just find them for now. Every time you find an important fact, turn it into a question. So the important fact, sound cannot travel in a vacuum, well that's very easy. You can turn that into, where can sound not travel? Or, can sound travel in a vacuum, to make it easier? And on the other side of the flashcard, you write the answer. So by the end, you should have a set of flashcards, lots and lots and lots of them, probably 50 or 60, with every important fact becoming a question, and on the other side there's the answer. Now ideally you'd make them earlier than you're currently making them, but actually the very process of making them is useful. It makes your brain work over the problem and think about how to word things as questions. It makes your brain think about the answers. But normally I'd recommend doing this much earlier and then using them for revision, because then in a few weeks later you can quiz yourself on these questions. So that's what you're going to do, and it's going to take you a little bit of time. It's probably again another 20 or 30 minute task. Carefully work through all your work, your notes, or if your notes are no good, your PowerPoints on student resources, which are on Teams, and identify facts and make them questions. By the end, you should have a set of flashcards which you could show me and you'll be able to show me, and that will be your revision for the sound topic. Fine. So pause me and get on with that. Right. So last topic now, and that is, we're back to the beginning. Metals and non-metals. Now, this is one of the easiest and one of the hardest. And the reason it's one of the easiest and one of the hardest is because there are some really easy topics which come up quite a lot, but every now and then you'll find a ridiculously difficult question. And those are the bits we're going to focus on now, for the days, just so you feel prepared. So I'm going to work you through with some questions. The final thing of this lesson, and these questions are going to be a quiz, and then some proper questions. So it's just going to be A, B, C, or D. I'd like you to write down A, B, C, or D, depending on what you thought. Now, some of them will be more than one, so it might be A and A or B and C. You see what I mean? So I'd like you to write down 1 to 14. I have missed some because there were some 2 different questions and I deleted them. So you will find some of them I missed, sadly. Write down 1 to 14. You're going to write A, B, C, or D, or more than one if you think it's more than one. So, let's get started. 1. Which of those is a metal? That's an easy question to start with. Is it A, B, C, or D? Have a look. Write down the answer. B, A, C, D. D, C, A, B. We'll go through the answers later. 2. Which of these is a property of metals? Again, a nice easy one. A, B, C, or D? Well, I was about to say, can't be, it could be more than one actually. It could be more than one. Question 3. Which of these is an element? Again, these first few are really easy. Question 4. Right. Which area of the periodic table has non-metals? Well, maybe this is a bit more difficult. Where are the non-metals here? Could be more than one. It could be B and C. It could be D and C. Question 5. Oh, doesn't exist. It was too difficult. Question 6. Which diagram shows an element? It could be more than one. Question 7. Doesn't exist again, neither does 8. Question 9. Metal and acid. What does it make? And this is a harder question. If you put a metal and an acid together, what thing will they make? Do they make carbon dioxide? Do they make salt? What do they make? Right. Alkali metal and water. Now, to be honest, it could be any metal. What do they make? Right. Metal and oxygen. What does it make? What does it make? Question 13. Hydrochloric acid makes something salts, sulfuric acid makes something salts. Now, you will know there's more than one here, there's 2, so pick the 2. Put them in the right order, please. Question 14. Sodium hydroxide plus hydrochloric acid makes what? Do you know what? I apologise. I meant to change this. Ignore question 14. I apologise for that. But that is a different topic entirely. I meant to, we need to change it to be something more useful. We'll go over questions just like this in a second. Don't worry about it. So let's go back and do the questions we can do. Question 1. Which of these is a metal? If you didn't answer it, pause it and answer it. Do that goes for all the questions. So which of these is metal? The answer is B, magnesium. B. All the others are non-metals. Question 2. Which of these is a property of metals? Well, do they conduct electricity? Yes, they do. That's very important. It could be others as well. Do they have a low density? No, they don't. They don't. They're actually generally very dense. Are they brittle? Do they shatter easily? Do they break easily? No, they don't. Not generally. No. They have a low melting point. No, they don't. They have a very high melting point. So, only A. Question 3. Which of these is an element? The answer? C. All the others are made of elements. All chemicals are made of elements. Hydrogen and oxygen make water, but carbon is the only element on its own. Where is the non-metals? Well, C is the answer to that question. A, B, and D are all metals. Most of the periodic table is metals. Only C is non-metals. And on your periodic table, you will be able to see when you look in your planner, it's this little staircase going down like this, and the non-metals end up over on the C side. Which of these is an element? The answer? C and D, and depending on what you said, possibly B. So, an element is one type of atom. One type of atom. So C is definitely an element. It's just one type of atom. It's a pink atom. I mean, in reality, they're not coloured, but that's how we've represented it. C is definitely an element because it's got one type of atom. D is also an element because it's only got one type of atom. It's only got the red ones. B is 2 elements. So if your answer was B because it's got elements in it, that's fine. A is a compound because it's got more than one type of element in it. Metal and acid. Right. Metal and acid make a salt, A, and hydrogen, C. A and C. They don't make carbon dioxide, they don't make water. Alkali metal and water, well, just any metal and water, makes metal hydroxide, B, and hydrogen, C. B and C. Metal and oxygen makes metal oxide, nothing else, just metal oxide. D. Right, hydrochloric acid makes B, chloride salts. So if I add hydrochloric acid to a metal, it will make a chloride salt, sodium chloride, magnesium chloride, potassium chloride. Sulfuric acid makes sulfate salts. Sulfate salts. If I add sulfuric acid to magnesium, we'll make magnesium sulfate and hydrogen. Fine. Question 14 we're skipping. Now, the final thing we're going to do today is this, and it's very difficult. Or is it? I don't know. Maybe you'll find it easy. I always found it very difficult when I was your age. So I anticipate that you will too. What I've got here is a series of word equations. I'd like you to try to do them without going back in your book or on bite size or looking it up at all. I'd like you to have a go. Now, I will actually provide a hint here. I think that will make your life easier. Now, if you don't want the hint, you might not want it, you might think you've got this, just pause me now and do the question. If you do want the hint, if you're looking at that going, I don't have a clue, then the hint will be coming up now. It's there. Now, sulfuric acid, if you add sulfuric acid to any metal, it will make a sulfate salt. Hydrochloric acid, well, if you add that to any metal, it will make a chloride salt. And nitric acid, if you add that to any metal, it will make a nitrate salt. So, I'd like you to have a go at this. Do the first three. And if you're not sure, I will go through the answers in just 1 minute for the first three, and then I'll give another gap, you do the next two. So off you go. Right. Let's have the first three answers then. So sodium plus hydrochloric acid. Any metal plus acid will make a salt and hydrogen. So you can write hydrogen down straight away for the first one. Make hydrogen and a salt. We need the name of the salt. What's the name of the salt? The name is sodium chloride. Sodium chloride. Sodium plus hydrochloric acid makes sodium chloride and hydrogen. How do I know it's sodium chloride? Well, sodium is the metal. It's always the name of the metal first. And then we just stick the name of the salt on here. So hydrochloric acid makes chloride. So sodium chloride, right? So let's do potassium and water. Well, if you add any metal to water, you make a salt. No, you don't. I apologise. You make metal hydroxide and hydrogen. So, potassium hydroxide plus hydrogen. And then rubidium and oxygen. Well, if you add any metal to oxygen, you make metal oxide. It's just rubidium oxide. So let's have a look at these two down here, then you can pause me again and have a go at them. Right, magnesium sulfate plus hydrogen. How do I make that? I'm going to use magnesium, perhaps obviously, but yes, magnesium is the first dotted one, and sulfuric acid, because it's sulfate, and sulfates are made by sulfuric acid. Well, something plus water makes calcium something plus something. Well, if I'm going to make calcium anything, I need calcium, so calcium plus water. Calcium plus water makes calcium what plus what? Calcium what plus water makes calcium hydroxide and hydrogen. And that's the end of that. It's just that simple. Is it simple? I'm not sure. Now, this is very difficult. If you don't follow this, if you're finding the rest of it difficult, I would leave this till last. If you've got the rest of this, you can go on to Bite Size, you can look up how to do these, or you can find questions of these on the PowerPoints and student resources. So, hopefully that's all been useful to you, gents. There's a lot we've got through there. But the test is tomorrow. Do not stress about that test. Do not worry about that test. Just do the revision you can in this lesson. If the lesson's not already over, not how long it took you to do the rest of the tasks. If the lesson's not already over, do the revision you can now. And then just come in and do your best on the test tomorrow. And I'll look forward to seeing you back in school tomorrow.